量子理论是当前物理学研究中最前沿和最活跃的领域之一，它对理解物质的基本性质和宇宙的工作原理具有深远的影响。当代量子理论最重要的基本问题之一是如何将量子力学与广义相对论结合，以解释包括黑洞、宇宙大爆炸以及宇宙早期条件在内的现象。解决量子理论与广义相对论的不一致，发展一个统一的理论，也就是量子重力理论，是当代物理学中最根本的目标之一。这一量子理论当前的研究动态怎么样？将来发展的方向如何？请听听当代著名物理学家彭罗斯、加来道雄、霍森菲尔德等对量子理论及其未来之谜进行的辩论。当代著名数学物理学家、诺贝尔奖得主罗杰·潘洛斯在数学物理领域的工作拥有高度评价，特别是对广义相对论与宇宙学的贡献。他一直在探索量子力学中的一些基本争议和挑战。在不久前的表述中，他表示他对量子力学成为科学中的终极理论持怀疑态度。他认为是因为量子力学所具有的内在的不一致性，特别是强调了薛定谔方程的决定论本质与波函数坍缩和波恩规则所引入的几率结果之间的困境。彭罗斯质疑对于量子力学的传统解释，这种解释将波函数坍缩与有意识观察者的观测联系起来。彭罗斯暗示解决方案可能在于将量子力学与广义相对论调和起来，特别是关注重力在坍缩过程中的作用。这种观点显示了对于传统方法的背离，主张采取创造性和创新性思维来发展一个更为连贯的理论。这样的理论将量子物理的决定性和几率元素与广义相对论的原理整合起来。
Let me backtrack a little bit. When I was talking about quantum mechanics, one of the problems is that the theory doesn't really make sense. Some people call it the best theory you've ever had in science. Maybe it is. I don't think it is myself, because it's it's inconsistent with itself. And this is because there's an equation called the Schrödinger equation, which tells you how the quantum state evolves. And it's very deterministic, like Laplace and all these other people. If you know what the state is now, and you know what the things you put into that is to say the matter or whatever it is you're talking about, what's called the Hamiltonian, you feed that in, then the Schrödinger equation gives you a deterministic evolution. If you know what the system is now, then in 15 minutes from now, you would be able to tell what the system is. However, it's not the whole story, because the matter doesn't satisfy the Schrödinger equation. When the system is nice and small and uncluttered, then it seems to. When it gets too big in some technical sense, which I could say more about, but not everybody agrees on what that means. When it gets too big in some sense, then it doesn't follow the Schrödinger equation. Schrödinger got very upset about this, quite reasonably. What it does is that the wave function, that's what the Schrödinger equation is talking about, how the wave function evolves, and the wave function is describing the world according to the theory. There is a thing called the collapse of the wave function. So it doesn't follow the Schrödinger equation. And usually this is considered by when something or somebody makes a measurement. Now, in the old days, it was quite often thought of that a measurement or an observation, the word observation was often used, that suggests that some being comes along and looks at the system, and that's making an observation on the system, and that's the point at which you collapse the wave function. Probabilities come out, it's not a deterministic equation anymore, and it's a thing called the Born rule, which you have to adopt. Instead of the Schrödinger equation, you change your mind and say, okay, well, let's use the Born rule instead. And this changing of the mind used to be considered to be the effect of a conscious observer coming and looking at the system, looking in a sort of broad sense. Now, my view is quite different from that. It's almost the opposite. I'm saying that there is something out there in the physical world which at the outset doesn't have anything, at least not manifestly, to do with consciousness. It's the way that the world operates, and this happens to do with what happens when you try to combine quantum mechanics with that other great theory of 20th century physics, Einstein's general theory of relativity. Now, you see, there's a good big school of thought which says, oh, well, we haven't brought them together yet. We need to quantize gravity. We need to bring gravity theory, Einstein's curved space theory of gravitation, you need to bring it within the scope of quantum mechanics. And that's the idea. Quantum mechanics is supposed to be the ultimate which you bring, but without mentioning that theory is inconsistent with itself. Now, my view is the opposite, that to make it into a more powerful theory, which agrees more with the way when it doesn't follow the Schrödinger equation, what does it do? That's when gravity becomes important. And there are arguments one can bring to indicate this is quite plausible. That when gravity becomes too important in your system, then the state does not follow the Schrödinger equation, and it starts to jump in the way that the Born rule tells you. You get probabilities, you don't get a deterministic evolution. Now, I do believe that that's where we should aim for, and that's where, if you like, creativity will come in, because we don't have the theory yet. So it needs creativity to go beyond current theories of physics, to introduce some new ideas which are indicated. You can see sort of aspects of the new scheme. It must have this effect and this and this. So you can see some things it's got to do, but we don't have the theory. Now, is that creativity? Well, it's creativity if it's not acting within the scheme that we had previously. Then you've got to be creative, because the theory we had previously doesn't give an answer here. It doesn't tell you what the collapse of the wave function is. It just says, you do it. And it doesn't say when, it just is a very incomplete picture. People like Einstein and Schrödinger and Dirac were a bit more polite than I am. They say the theory is incomplete. I'm saying the theory is actually self-inconsistent, so I'm a bit ruder than they were. But it needs something to be done, and that's where a bit of creativity absolutely is necessary. Well, I think the trouble with string theory is that there isn't any connection with observations. As far as I'm probably taking too strong a view here, but the mathematics, I mean, it's largely driven by the mathematics as far as I know, which is in itself is not an objection as far as I'm concerned. A lot of what I do is driven by the mathematics. But the trouble with string theory is it's supposed to be a theory of the way the world operates. And if the number of dimensions of space is just wrong, I can't take it seriously.
英国的数学物理和哲学巨匠罗杰·彭罗斯，还有美国的理论物理学超级明星加来道雄，都在当代科学的大舞台上担纲重要角色。彭罗斯因为挖掘黑洞的秘密而被人赞誉，加来道雄则以他对弦理论的深入贡献闻名遐迩。但有意思的是，彭罗斯可不买加来道雄的弦理论的账，对弦理论彭罗斯可是强烈反对的。
If you could have a theory which had predictions, and these predictions could be seen to be right or wrong, that's what I understand about physics. But string theory seems to me driven largely by certain ideas which have importance in mathematics, but sort of irrelevant to the physics, really. As far as I know, there's places where string theory has had an impact on mathematics. Sure, it has, but it's not physics, as far as I can see. So the main trouble I have with string theory is I don't think it's physics.
加来道雄认为，弦理论具有相对于其他物理学理论架构的独特性和优越性。他指出，弦理论的替代理论未能提供对宇宙的全面理解的三个主要原因：一、爱因斯坦理论的结合，任何可行的理论都必须与爱因斯坦的广义相对论完全结合。虽然有几种理论可以实现这一点，但这只是一个起点。二、 与标准模型的兼容性，这是许多竞争理论失败的地方。粒子物理学的标准模型包含36个夸克和反夸克、3代粒子和20个自由参数，是一个复杂的框架。任何旨在描述宇宙基本性质的理论都必须适应这个框架。加来道雄表示说，只有弦理论已经证明了完全包含标准模型的能力。3. 量子异常和发散的处理。当试图将量子力学与经典物理学统一时，许多理论都会遇到异常和发散的问题，即计算产生无限或未定义结果的情况。超对称是弦理论固有的组成部分，也是有效管理这些问题的唯一已知机制。加来道雄认为圈量子引力作为另一种理论存在有缺陷，特别是它无法将物质，例如电子，纳入其框架中，这使得它与万物理论缺乏关联。加来道雄强调发展理论所面临的挑战，它不仅可以解释时空的结构，还可以解释占据时空的粒子。他主张对理论物理学采取多元化的方法，鼓励多种理论的发展和比较，以突破我们理解的界限。他强调，对任何万物理论的最终考验是其整合标准模型以及控制分歧和异常的能力。透过这些衡量标准，弦理论成为目前唯一能够满足这些标准的框架。加来道雄的立场凸显了物理学界内部关于寻求统一理论的最佳前进道路的持续争论。虽然他承认弦理论尚未被证明是正确的，但他将其定位为寻求统一自然基本力和构成宇宙的粒子的主要竞争者。这强调了理论多样性在科学进步中的重要性，同时也指出了替代理论必须克服的重大障碍，才能挑战弦理论的主导地位。
Well, so far all the theories that have been put up that are rivals of string theory have failed. They failed for basically 3 reasons. First of all, the theory has to incorporate all of Einstein's theory, which they can do. Second of all, they have to accommodate the standard model. And that's where a lot of these theories fail. That means 36 quarks and antiquarks, 3 generations of identical subatomic particles, 20 free parameters. That's the standard model. Only string theory has the richness to describe the standard model. And third, which is the real killer, is that once you combine quantum mechanics with classical physics, you get anomalies, divergences, things blow up in your face. The only way we know to control these divergences is through supersymmetry, which is the symmetry of strings. In other words, string theory has no rival. I repeat, string theory has no rival. Other competing versions do not have the standard model or they diverge. Take a look, for example, at loop quantum gravity, which is a very interesting theory. I've looked at it. Loop quantum gravity has a problem. It has no electrons, which means it has no matter, which means it's a theory of pure space, which means it's kind of useless. It's a theory of pure space with no electrons, no standard model, none of that. And that's why string theory is different. String theory can accommodate the standard model. My attitude is, let 1,000 flowers bloom. Let all of them bloom, mature, so that we can pit them against each other, okay? We're not going to hurt anyone's feelings. These theories have no feelings. So let them clash, and let's find out the limitations of these things. Loop quantum gravity has a problem with fermions. The fermion loops are divergent. They blow up in your face. The only way known to cancel these divergences is through supersymmetry, which is the symmetry of strings. So in other words, we're still back to ground zero. that loop quantum gravity does not have a theory with fermions that have finite results. And so what I'm saying is something very simple. You can read alternative versions that claim to have the theory of everything. Fine. But the acid test is to look for whether or not they can incorporate the standard model and whether or not they can control the divergences and anomalies. And so far, string theory is the only one which can do this. Now, that doesn't mean string theory is right. It just means it's the only game in town.
法兰克福高等研究院理论物理学家、著名物理学博主萨宾·霍森菲尔德认为，量子力学与广义相对论之间的不一致性的核心问题在于，虽然4种基本力中的3种电磁力、强合力和弱合力展现出量子属性，但由爱因斯坦的广义相对论描述的引力却没有。这个差异提出了一个深刻的问题：如果像电子这样的量子粒子可以同时存在于多个状态或地点，那么它们的引力影响如何表现呢？鉴于广义相对论不考虑量子现象，这些量子状态的引力场就成了一个谜。他强调说，描述量子粒子合力的量子场理论与广义相对论之间的数学不兼容，突出了我们对宇宙理解的重大缺口。这个缺口标志着需要一个量子引力理论，这是一个能够无缝整合量子力学与广义相对论的统一框架。虽然弦理论和圈量子引力是解决这一挑战的最主要尝试之一，但还存在其他较不主流的想法，如渐进安全引力。反思几十年来众多杰出思想试图调和这些基本理论却未获明确成功的努力，霍森菲尔德建议采取谦逊和开放心态的方法。他质疑问题可能不在于引力，而在于我们对量子力学本身的理解，提出探索量子化的替代概念化或调查这种不一致性的量子方面可能提供洞见。此外，他主张多样化研究努力，包括修改引力理论或探索诸如涌现或诱导引力的概念。霍森菲尔德表示，不应将我们所有的理论赌注放在单一方法上的重要性。相反，他支持广泛且包容性的探索潜在解决方案，以解决物理学中的这一根本问题。它体现了统一描述宇宙中非常大广义相对论与非常小量子力学的理论的复杂性，以及在追求对宇宙更深层理解的过程中需要创新思维和对广泛理论探索的开放性。
We know of 4 different fundamental forces in physics. That's the electromagnetic force that most of you have probably heard of. Then we have the strong and weak nuclear force, and we have gravity. And the problem is that 3 of those forces, the electromagnetic and the 2 nuclear forces, have quantum properties. So we have some particles like electrons and quarks and gluons, stuff like this. And we know that they do funny things, like they obey the uncertainty principle, they can be in 2 places at the same time, that kind of weird stuff. And then there's gravity, which is described by Einstein's theory of general relativity, and that theory doesn't know anything about quantum properties. And this brings up the question, if I have a particle like an electron that can be in 2 places at the same time, and it has a mass, and that mass generates a gravitational pull, where does the gravitational pull go? You'd expect that to also go to 2 places at the same time, but Einstein's theory can't make that work because it doesn't know anything about quantum properties. So this leaves us in this weird position where we just don't know what the gravitational pull of an electron is. So it's a really simple question, like what's going on with the gravitational field of this electron, and we don't know. And if you ask like more technically what's the matter, it's just that those 2 theories the quantum field theories that we use to describe particles, like the electron and a couple of other particles, Einstein's theory of general relativity, they're just mathematically incompatible. If we just put them together, it doesn't work. But nature knows how it works. So there's got to be a solution to this. And we don't know what it is. There have been many people who've tried to solve this problem. What we need is a theory of quantum gravity, so a theory that gives properties to gravity. At least that's the way that it's normally put. But more generally, we need some way to resolve this discrepancy between the two theories. And the probably best known approach to this is string theory that most of you will have heard of. There are other ideas like loop quantum gravity, and then there are less well-known ones like maybe asymptotically safe gravity and stuff like this. But so far, we don't know if any of those is correct or how we can even test them. And yes, I think it's a really big problem. Now, when it comes to my personal opinion on what to do, as I just said, like, people have worked on this problem for a long time. It's been known since the 1930s or something, so it's definitely not a new thing. And there are lots of smart people who have spent their whole life trying to fix something that they think is wrong with gravity. And I have a lot of respect for all those people, and if they couldn't make it work, I'm pretty sure I can't make it work either. So this is why I think it's a better strategy to try and figure out if not there's something wrong with the quantum side of things, that the problems may be caused by us not understanding what quantization means in the first place. I generally think it's not good to put our bets on one thing. So I'm really supportive of spending some time on modified gravity and different approaches to that kind of thing. Spending some time on the idea of trying to replace gravity or explain it as something emergent or induced gravity. This is a similar but related idea. Or maybe just saying maybe the fault is with the quantum side of things, which is what I personally work on.